The Earth's core is mostly made of heavy metals like iron and nickel, whereas the crust, the outer thin crust, is made of the lighter silicates. Why is it like that? Why are the heavy stuff close to the center, whereas the lighter ones are closer to the surface? And if you consider extremely cold places like, say, Antarctica, the average temperature over there is close to minus 50 degrees Celsius, which is way below the freezing point of water. And yet, for some reason, the oceans and the lakes do not freeze over there. And that's why aquatic life survives. But why don't they freeze? Well, to answer this question, we need to dig deeper into the idea of fluids and densities. And that's what we're going to do in this video. So let's begin. So what exactly are fluids? Fluids are substances that flow, and they do that because they don't have a fixed shape. So think about liquids and gases. Collectively, we call them fluids. And if you consider our planet, most of the surface of the planet is covered with liquid water. That is a fluid because water can flow, rivers and oceans all flow. And what about our atmosphere? Well, it's air, which is a gas, which is also a fluid. Because again, we know that it flows, giving us air currents and breezes and storms and whatnot. In contrast, if you consider the solid surfaces over here, they do not flow because they have a fixed shape. Now, of course, over very large time scales, they too can flow because of geological processes, but we're going to ignore that, okay? Solids do not flow because they have a fixed shape. But why? Why do solids have a fixed shape? To answer that question, we need to zoom in at the atomic or the molecular level. If you could zoom into a solid, like for example, ice, the molecules experience a force of attraction that makes them stick to each other. But they also have a thermal motion, which makes them move away from each other. Now in solids, the thermal motion is low enough that the attraction wins. And as a result, molecules and atoms end up sticking to each other, giving them a particular shape. However, when you consider the liquid phase of that same substance, the temperatures are relatively higher. So thermal motions are relatively higher, high enough to partially overcome the attraction, because of which they no longer are able to retain the shape. That's why liquids tend to take the shape of the container. And what about the gas phase? Well, here the thermal motion is so high that it completely overcomes the attractive forces, because of which the particles are pretty much moving freely. So look, in liquids and gases, the thermal motion of the molecules can overcome the attractive forces. That makes them flow. All right, so fluids flow. What's the big deal? Well, the big deal is because they flow, when you mix two different fluids, or a fluid and a solid, they can sink or float. And that has a huge consequence, as we will see. But what decides whether something sinks or floats? Well, that depends on an important property called density. You can think of density as a ratio of mass and volume. So the standard unit for density would be, well, mass is in kilograms and volume would be meter cube. So density's standard units would be kilograms per meter cube. But what exactly does it represent? Well, think about density as a measure of how crowded something is, or how packed something is. How much mass is packed in a unit volume. How many kilograms are packed in a meter cube? Or, a more convenient unit would be how many grams are packed in a centimeter cube. Whatever it is, it's a measure of how packed something is. So let's take some examples. If you take water, for example, it has a density of 1,000 kilograms per meter cube. So you can imagine a meter cube of water contains 1,000 kilograms of water. But again, I like to think in terms of grams per cm cube. That's more convenient. So if you convert this, you end up with 1 gram per cm cube. The idea is the same. If you now take a centimeter cube of water, it will have a mass of 1 gram. In contrast, if you consider iron, it has a density of 7.8 grams per centimeter cube. A centimeter cube of iron has 7.8 grams of iron packed into it, which is much higher density compared to water. And by the way, if you're wondering whether this is a coincidence that the density of water is exactly 1 gram per centimeter cube, such a nice number, it's not a coincidence. We defined our gram this way. The mass of 1 centimeter cube of water, by definition, is 1 gram. But anyways, if you consider water or iron for that matter, the densities are uniform. It's the same everywhere, which means if you take a small amount of water here or a large chunk of water over here, the density will be the same, 1 gram per centimeter cube. Similarly, if you take a small chunk of iron from here or a big chunk of iron from a ship, for example, the density would be the same, 7.8 grams per centimeter cube. But that's not always the case. If you consider the density of the air, for example, close to the surface of the Earth, it is roughly about 0.001 grams per cm cube. You can see the density of the air is much, much smaller than that of water. It's about 1,000 times smaller. However, If you consider the density of the air, at say about 10 kilometers, which is usually the cruising altitude of a commercial airline, you would find the density even lower, 0.0004 approximately grams per centimeter cube. And in fact, the higher you go, the smaller the density. But why? Well, think about it this way. If you consider the layer of air over here, it's carrying the weight of the atmosphere on top of it. That weight is pushing down on the molecules over here, squeezing them together, packing them together, giving them a specific density. But now if you consider a layer of air that is even lower, then look, it's carrying an additional weight compared to this layer. So it's carrying more weight. In fact, the layer at the bottom carries the entire weight of the atmosphere, and therefore the forces are much higher, and so the molecules are squeezed together much higher, packed together more tightly, giving you a higher density, and that's why the lower you go, higher the density. But wait, shouldn't the same be the case with water as well? For example, if you consider the ocean, then shouldn't the layer at the bottom of the ocean have a higher density than the layer at the top of the ocean? Well, that's a great question, but turns out not to be so because of one main difference between liquids and gases. Gases can be easily compressed. And to demonstrate this, here's a syringe, which contains only air, and I've sealed the top with my finger. Now, let me try and push it, and you can see I can easily compress it. I have compressed the gas, and I've increased the density just by using my finger. But now let's see what happens if you fill the syringe with water. Again, seal the top with my finger, and now if I'm pushing it, look, I can't compress it even a little bit. I am pushing as hard as I can. It's just not possible. So this means liquids are extremely hard to compress, and because you can't compress them, you can't squeeze the molecules closer, and you can't increase the density. And so that's why even though at the bottom, the pressures are insanely high compared to the top of the oceans, in fact, the pressures at the bottom are so high that even submarines can get crushed. But because compressing water is extremely difficult, the molecules will not come any closer than they are at the top, and as a result, the density is pretty much the same everywhere. And so we would model water as an ideal fluid which is incompressible. I mean, technically, you can compress water if you put horrendous amounts of forces, but since we're not dealing with such high forces, usually we can model it to be incompressible. So ideal fluids are incompressible, and they also have no viscosity. What does that mean? Well, some fluids can be very thick, making them very hard to flow. Think about ketchup or honey, for example. Because of their thickness or viscosity, it can produce resistance to motion. But when we're dealing with ideal fluids, we model them by saying that, hey, ideal fluids have no viscosity at all. All right, now let's try to explore why stuff sinks or floats when we mix fluids or fluid in a solid. So let's see what happens when you mix water and oil. What we notice is that if you allow them to settle, oil floats, or you could say that water sinks. But why? Well, first of all, we can easily model them as ideal fluids because the density is pretty much the same everywhere. What you would find now is that oil has a density that's less than that of water. So stuff that has less density tends to float. Or you could say that water has a density more than that of oil, and therefore it sinks. Stuff that has more density tends to sink. Let's take another example. If you put an iron bolt in water, it sinks. Why? Because we already saw iron has a much higher density than water. What about ice? Ice floats on water because it has a less density than water. Here's another way to think about it. Here, the gravitational field is acting downwards, isn't it? So stuff which has more density tends to move in the direction of the gravitational field, sinking, and stuff that has less density tends to move against the gravitational field. What's interesting is that without the gravitational field, we wouldn't have flotation or sinking. And it's for the same reason why helium balloons tend to move up, because they have a density that's less than the surrounding air, and therefore they move up against the gravitational field. Okay, now let's see if we can use this to explain our original question about the Earth. When the Earth was formed, we believed that it was highly molten, and so we can model them as as an ideal fluid. Now, in this fluid, the gravitational field acts towards the center. So stuff that is having a high density, like iron and nickel, they will tend to move along the gravitational field, sinking and eventually settling towards the core. On the other hand, stuff that has lighter, lower density, like the silicates, for example, tend to move against the gravitational field. They tend to float, and that's why they settle near the surface. And that's why eventually, when this molten rock cooled to form the Earth, the core ended up having high density heavy metals, and the crust ends up having the silicates. Amazing, isn't it? Finally, we go back to water. We know that ice floats on water, but that's a little weird if you think about it. Because whenever you cool something, the molecule tends to have less thermal motion, because of which they tend to come closer together. So the density actually increases when you cool stuff, generally. Okay, that kind of makes sense, right? So in reality, density depends on temperature. And the same thing works for water. As you cool down water, its density will keep increasing until we reach 4 degrees Celsius. Guess what? Turns out that water has a maximum density at 4 degrees Celsius, and that maximum density is 1 gram per cm cube. So we should have actually told, that water's density is 1 gram per cm cube, or 1000 kilogram per meter cube, whatever you want to think of it as, at 4 degrees Celsius, because density does depend on temperature. But wait, what happens if you cool down water below 4 degrees Celsius? Well, now molecules will have such low thermal energy that they lock in places, and look, in doing so, they start forming gaps in between, which reduces the overall density. And that's why density tends to decrease below 4 degrees Celsius. And eventually, as water crystallizes into ice ends up having lower density than water, and therefore ends up floating. And this has a huge consequence on the aquatic life in really, really cold places. So if we go back to our Antarctica, for example, we can model water by considering 3 different layers, okay? Let's say the current temperature is about 6 degrees Celsius, okay? Now, what if the temperature outside reduces to 5 degrees Celsius? What's going to happen? Well, the surface of the water, which is in direct contact with the surrounding, that is first going to lose heat, and as a result, reduce its temperature to 5 degrees Celsius. Now, because it is colder, it has a higher density, and as a result, it will sink below the other layers. And now this one will, cool down to 5 degrees Celsius. It gets colder, it gets higher density, it will sink, and eventually the last layer will come on top. So this is how we can model how extremely large water bodies cool down. Now, if the temperature gets lower to say 4 degrees Celsius, again, the same thing repeats, and the whole ocean now is at 4 degrees Celsius. But at 4 degrees Celsius, remember, we have maximum density. Now, if the surrounding temperature goes below 4 degrees Celsius, let's say 3 degrees Celsius, again, the top layer will go down to 3 degrees Celsius because it's in direct contact. But look, now the density is lower than the layers below, which means it cannot sink. It will keep floating, and these layers will not have a chance to come in contact with the surrounding layer, and therefore relatively they will stay warm, pretty close to 4 degrees Celsius. And now, as the temperature keeps dropping, this is the layer whose temperature will keep dropping, keeping the lower layers warm, and eventually this layer will crystallize. And now it doesn't matter how cold it gets outside, the lower layers are protected. And this is why only the top of the water body tends to get frozen, and the bottom will stay relatively warm, and it will stay in the liquid form. It allows aquatic life to exist.